Okay, on to chapter 5, and we're talking about the introduction to solutions and aqueous reactions. And remember, this is just the intro. Some other places we go a little bit more in depth. Starting off, the hook in the book was talking about molecular gastronomy and its way of preparing food that involves chemistry. And the common reaction is precipitation with this. And in a precipitation reaction, which we will talk about later in this chapter, is when you have two solutions that are homogeneous mixtures. They have compounds that dissolve in water, but when you mix them, a new compound forms that no longer dissolves in water. And that compound that is not soluble in water anymore is called a precipitate. And it also falls. It falls from solution. And so this is something, and you can use something called spherification to encapsulate liquids is another one, so you can get flavors stuck in there. So, and we, spherification is kind of already done in our bodies and biological systems as well, like cell membranes, for instance. So let's talk about concentration. And so you can take a simple solution like salt and water to form a homogeneous solution. And so these mixtures are called solutions, and they don't always have to be liquid. An alloy, for instance, is a solid solution. Whatever you have the most of is called the solvent. Whatever you have the least of is called the solute. And you can have more than one solute. So ocean water, for instance, water is a solvent, and there are several different salts that are the solute. Also, gases dissolve in water as well, so it can be things of different phases, although the solution is one phase. And any solution that involves water is called an aqueous solution, and there's quite a bit of them right here, especially here on Earth and dealing with biological stuff. So, in concentration, so we can have dilute and concentrated solutions. So I always think about orange juice, right? So you buy the tube of orange juice from the grocery store, and it calls it orange juice concentrate. So it's the same amount of orange juice goodness, but concentrated into a smaller frozen tube, right? So the idea is concentrated solutions have more stuff, diluted solutions have less stuff per volume. And the relative amount of the solute is if there's more solute, we call that a concentrated solution. So the relative amount is the concentration. And in chemistry, what we use is a concentration term called molarity, and that is moles of the solute, what is dissolved, over the volume of the solution in liters. So that is the molarity, oftentimes indicated by a capital M. So for instance, this is how you would make a 1 molar sodium chloride solution. You take 1 mole of sodium chloride, which is 58.44 grams, and then add the water up to 1 liter. So the total volume of the solution is 1 liter. And later on, in future chapters, we'll talk about there's other concentration units. There's percent by mass, percent by volume, and things like molality. That's moles per kilogram. That's a different unit. So there's other forms of concentration, but molarity is used very frequently, especially in chemistry class. But it's also it's a weird sort of bulky unit. So typically, if you work in industry, you'll get something else, like especially in a factory where they make things. They'll just give you like add this much. It's usually in mass or volume when you make things in huge quantities. Okay, so let's do this. How many moles of solute are required to make 3 liters of a 2 molar solution? So 2 molar means 2 moles per liter. 2 moles per liter times 3 liters, that's going to be 6 moles. So that's using the dimensional analysis. So let's use some molarity and calculations. And I just showed you there in the previous example using dimensional analysis. And so if you dissolve, but don't get ahead of yourself on something though. If we dissolve 25 grams of salt and 251 grams of water, what is the mass of the solution? So don't forget about volume and mass. Here, 25 plus 251, this is just simple addition of mass. So be careful when you think too much in moles. And also look, when you have a problem like this, look to see what things are being asked of you. So frequently when you buy things, especially in the chemistry class, you have stock solutions that have very concentrated things. Like, for instance, sulfuric acid is typically sold in 18 moles per liter. And then when you make new solutions, say I need a 1 molar solution, well, I'll take that 18 moles per liter and I'll just dilute it. And using this equation, molarity, capital M of 1 times volume of 1 equals the molarity of the second, volume of the second. Sometimes instead of M, you can see C. That's very common for many textbooks and laboratory manuals to have C instead of M. So be aware of that if you see these in different textbooks or different books. So how do we get a 3 liters of a half molar solution from a 10 molar stock solution? Well, we have to figure out how much to, well, I mean, it's already shown you there. You would just use an unknown, just use simple algebra. So molarity of 1 is 10 molars, volume of 1 is our unknown, equals molarity of second, volume of second. Molarity of second is half molar, volume of second is 3 liters. So you would take half a mole times 3 liters divided by 10, and then that would give you the 0.15 liters. So solving for that unknown variable. Also, don't forget that reaction stoichiometry. Remember, stoichiometry is the chemical accounting, and you have to use the coefficients in balanced chemical equations. So keep that in mind as you do your calculations. For instance, here, if we have this reaction, 2A plus B makes C, all aqueous. What is the limiting reagent if you have a 1 molar A solution, 1 molar B solution? Well, you need twice as much A as you do B, so that would be the A would be the limiting reagent and B would be in excess. So let's talk about the different types of aqueous solutions and their solubility. And we're very familiar with salt water and sugar water. And they're both homogeneous mixtures. Sugar water, that's sucrose sugar, that's the most common one, stuff when you buy from the store. There's other sugars, but sucrose, that's table sugar. And what happens? What happens when you throw it in water and they disappear? Well, and this is something we're still doing research on, especially when it comes to chemical reactions. But the reason why it dissolves is that the attraction between the solvent and the salt, so the solvent and the solute is if it's greater than the attraction between the solute and the solute itself, then it will dissolve. But if it's weaker, it tends not to dissolve. It can still dissolve a little bit because there's a driving force called entropy or disorder. So in certain cases, you can get things dissolve even though it's not energy favorable. So icy cold packs work off of that principle. So when you hurt your arm and you use the icy cold packs and you break it and you put it together and it gets cold, that's the enthalpy, the heat released of the dissolving of the solute. It's energy. It absorbs energy, so that's why we use it there. So, but generally speaking, it's energy favorable. And water, how is it energy favorable? Well, jumping quite ahead, water is what we call a polar molecule. The oxygen end of the molecule has a slightly negative charge, and the hydrogen end has a slightly positive charge. And what do I mean by slight? I mean less than 1.6 times 10 to the minus 19 coulombs. And that is the charge of a proton and an electron, a negative electron, respectively. So if it's smaller than that, and then, so this is known, since there's two ends of a molecule with different charges, we call that polar. And that means that the sodium ion, the sodium plus 1 ion, is attracted to the partial negative charge of the oxygen, and the chloride anion is attracted to the partial positive charge of the water. But this is only a partial charge. The sodium and chlorine have a very strong bond. So how does it overcome this? Well, the answer is more surround it. So typically speaking, for sodium chloride, it's 6. And 6 is a very common coordination number. That's the amount of stuff. The coordination number is the amount of stuff that surrounds something. It's usually either 4 or 6 are the most common numbers, because 4 forms a tetrahedron, 6 forms an octahedron. And So the idea is that the 6 times that partial charge is actually stronger than the individual charges within the salt crystal. And other things dissolve and interact with each other with solutions. I told you we're still studying this. There's a certain type of reaction called an elimination reaction in organic chemistry. It seems like this can only be done in the liquid phase because the solvent actually stabilizes the molecule, stabilizes specifically the transition state. But I mean, that's the research we're doing now, and that's interesting, of course. But I'm a chemist. So let's talk about different types of solutions, specifically electrolyte and non-electrolyte. So electrolytes, so sports drinks have electrolytes, and what makes them electrolytes? Well, they conduct electricity. Essentially, they have salt, usually sodium chloride. Sometimes they put potassium salts into sports drinks, but it's usually sodium salts. And with that, water is a very weak, pure water. Pure water is a very weak electrolyte, even considered to be a non-electrolyte. Water does conduct electricity a little bit, pure water at least, but it's not very it's not a very good electrical conductor. But there are certain things like sugar. If you add sugar to water, it does not make the water conduct any better. But then you add something like salt, and then the solution conducts very well. And that means that salt is an electrolyte. And so we have electrolytes, or strong electrolytes. We have non-electrolytes like sugar, we've already mentioned. And then we have weak electrolytes. So weak electrolytes, so if you look at, so salt, for instance, completely breaks apart. Strong acids break apart, but and strong bases too. Weak acids and weak bases, though, they tend to stay molecular. They tend to stay together. So we have acetic acid in the bottom beaker here, and that's a weak acid. And so well, let's talk about the interaction. Sucrose, you see, it doesn't break apart at all. It stays completely molecular. And so complete ionization. These are strong acids. They come to the water party and they break apart. The weak acids, though, they come to the water party in solution and they tend to stay together. So the weak acids, I think of them like the disgusting couple. They're always together, holding hands. They're never far apart from each other. That is like a weak acid. The strong acids are like casual friends. They come to a party and they just leave, and then they're like, all right, we're here, bye. And then we don't have to see each other. It's cool. It's a party. Go mingle with you. If you find your friends, I'll find mine. But then weak acids, on the other hand, they're the ones that are clingy. They stay together the whole time. And so acetic acid, already mentioned, that's a weak acid. Hydrofluoric acid is another one. Nasty stuff, hydrofluoric acid. But it is also a weak acid. So strong electrolytes, these, like I said before, completely dissolve. So ionic compounds that are soluble and strong acids. And weak electrolytes, these are weak acids and weak bases. These can conduct electricity, but not very well. And this image shows that. We have the leads of a solution here, and it's a non-electrolyte, and it does not conduct electricity. A weak electrolyte, like it looks like vinegar, that slightly, it is vinegar. Huh. It does slightly conduct, and then a strong electrolyte, like sodium chloride, the light bulb shows bright, glows bright. It's very good conductor electricity. So which one of these solutions conduct electricity well? And the answer is the ionic solution, potassium bromide. B is glucose, that's another sugar. And then methanol. Actually, methanol is a worse conductor than water. So water, that would be a very non-electrolyte solution. I know it's probably saying a weak acid, but that's not a weak acid. So KPR. Okay, so let's talk about the solubilities of ionic compounds. And remember, chemistry is a observational science. So these are just the rules we've observed. And soluble means it dissolves in water. Insoluble means it does not. So, and I should talk about the general rule of this. The general rule of these, generally speaking, the bigger, lower charged ions tend to be soluble, and the smaller and highly charged ions tend to be insoluble. And the reason for that is, in order for something to become soluble, the attraction between the solvent, generally speaking, has to be stronger than the attraction between the solvent itself. And if you have small ions, and so the way that electricity works, like, so the smaller the charge ratio, so if it's a really concentrated charge in a small area, that's going to have a stronger attraction than a small charge that occupies a large amount of space. So that's the general rule in that. So you're going to see the soluble materials tend to be one or more of the ions are going to be low in charge. So for instance, if we mix silver nitrate in water, it dissolves. And silver chloride, though, it's completely insoluble. So these two things, these do not, so silver chloride is not going to dissolve at all into water. And I already mentioned, I kind of mentioned how we know salts dissolve, and it's a little bit advanced at this stage in the game because we haven't talked about the sizes of ions and molecules and that kind of thing, but I wanted to give you the general idea. But we've just gone through, and since chemistry is a empirical science, so we have gone and figured out the rules. So here are the rules. Generally speaking, alkalis and ammonium ions are always soluble, no exceptions. Nitrates and acetates, these are always soluble. Notice that the alkalis in these, we haven't talked about size of atoms yet. These alkalis are very light. They're not dense elements. And so they're very diffuse charges with very weak charges too, just plus ones of the alkalis. And ammonium, NH4, that is a molecule. It's a group of atoms, so it has 5 atoms with a positive charge distributed between it. So that's a very large area of the weak charge. Same thing with nitrate and acetate. These are polyatomic ions. They include several atoms and -1 charge distributed throughout these atoms. As such, there's a very diffuse charge. It's not going to have as strong of an ionic bond. Also, generally speaking, the halide ions, these tend to be insoluble, with these exceptions to the rule: silver, mercury, and lead. So silver +1, mercury 4 +2, or lead +2. And those are insoluble. And sulfates tend to be soluble with the exception of the alkalis, alkaline earths such as strontium and barium, and calcium and silver and lead. So these are the exceptions. These tend to be insoluble, generally speaking. Hydroxides and sulfides tend to be insoluble, with the exception of the alkalis and ammonium ion. So we've already mentioned before, there's no exceptions to that. And the sulfides with the alkaline earths tend to be soluble. And when the hydroxide pairs with the alkaline earths as well, it tends to be slightly soluble. And then carbonates and phosphates, these tend to be insoluble with the exception of the alkalis and the ammonium ions. So, and you can see as you get these larger charges, it's harder to get these things to dissolve. So let's look at here, which of the following of the compounds, which one of the following ions within a compound is going to show that there's always soluble, and the answer is nitrate. From the rules, nitrates are always soluble. And precipitations, reactions, I mentioned before, we have 2 solutions, you mix them together, and then a new compound is formed that's no longer soluble, tends to fall to the bottom, and that is called the precipitate. And for instance, if you have potassium iodide and lead nitrates, remember nitrates are always soluble, alkali, potassium are always soluble, you mix them together, but lead iodide, so the halides, the halogens, they tend to be soluble, and lead +2 is an exception, so that forms this lead iodide, lead 2 iodide precipitate. And sometimes, so like potassium iodide and sodium chloride, mixing these together, you think, oh, there's going to be a reaction. And no, nothing happens. No precipitation just means no reaction. These things just do not form a new compound. And so how do we predict them? You have to pair up the positive ions, the negative ions, and vice versa. So, and then you have to look at those ions and determine if one of them is insoluble. So that's the general idea for this. And if neither of them are insoluble, then it's a no reaction. If one is insoluble, then that's the precipitate, and you indicate where everything is dissolved in the aqueous form. That becomes the solid form, and then you got to balance the equation. So let's look at here. So if you look at potassium iodide and lead nitrate, the positive potassium ion can interact with a negative nitrate, and the positive lead plus 2 can interact with the negative iodide. And then you have to look at see what if any of them are soluble. So potassium nitrate, all nitrates are soluble. That's soluble. Lead 2 iodide. So halogens, halides tend to be soluble, but lead plus 2 is listed as one of the exceptions. Therefore, lead 2 iodide is insoluble. And then that's going to form the precipitate. So, okay, and how we represent them. So let's look at the precipitation here of magnesium hydroxide. So 2 potassium hydroxides plus magnesium nitrate in solution forms 2 potassium nitrates and magnesium hydroxide solid. And this is balanced, and this is known as the molecular equation. But we can dissolve the species into a complete ionic equation, and then we write everything out showing the ions. So it was 2 potassium hydroxide in the molecular equation. So it's 2 potassium ions, 2 hydroxide ions, magnesium plus 2 nitrate anions in the reactant side form the products, 2 potassium ions, 2 nitrate ions, and a magnesium hydroxide precipitate indicated by the solid. So, but notice something. Well, for here, the potassium and nitrate, they're on both sides of the equation. We call these spectator ions. So in the complete ionic equation, when you see ions on both sides of the equation, these are known as spectator ions because they don't directly participate in the reaction. Do they participate? Yeah, they provide countercharges to the reactants, so they do something. But they're there in one form on one side of the equation. They're there at the other form on the other, and the same form on the other side of the equation. So we say they're spectators. They don't necessarily actively participate in the precipitation reaction. So we can cross them out, and then when you do this, you get what's known as the net ionic equation. The net ionic equation. This is the so what. This is the Cliffs Notes or the Spark Notes. This is the Wikipedia article of the book that you want to read, right? So you don't want to read Macbeth, so you look up the article on Wikipedia, or you read the Cliff Notes, and then you hear about just the basics of the play, and then you go and you write your paper and hope that that's good enough for an A, right? So that's how we use the Cliffs Notes, the Spark Notes, and the various summaries on the internet. This is the net ionic equation. That's the summary reaction. That's the executive summary. So this complete net ionic equation tells us a story. We have lead plus 2 ions and 2 nitrates that have dissolved in solution, and we mix it with 2 potassium and 2 chloride ions, both dissolved in solution. Then the lead 2 and the chlorine minus come together to form the lead 2 chloride precipitate with the 2 potassium, the 2 nitrate ions floating in solution beside it. That is the long, drawn-out example of the net ionic equation. Now let's do the simplified version. Lead plus 2 ion mixes with 2 chloride ions, makes lead 2 chloride precipitate, done. So that's the net ionic equation, just the shortcut to the end. So let's summarize these. The molecular equation, and this kind of tells you, in a way, it tells me how it's formed. So it says the forms of the reactants. A complete ionic equation shows everything dissolved. The net ionic equation is just what's happened. It's just the quick and over, done with. So listed below, look at this equation here, which is the spectator ion. So looking at this on both sides of the equation, we have two spectator ions. So we have nitrate and sodium on both sides of the equation. So, and of the choices B, it's the nitrate. So other types of reactions, acid-base reactions and gas evolution reactions. So acid-base, sometimes referred to as neutralization, sometimes called acid-base neutralization, and they neutralize and they produce water or sometimes a weak electrolyte, depending on what it is. So gas evolution, it's a gas is produced, oftentimes bubbling. In old school, precipitation reactions were shown with a down arrow, and a gas evolution reaction was shown with an up arrow. And oftentimes, acid-base reactions and gas evolution reactions are one and the same. So you can have more than one type. So, okay, so let's talk about acids. Acids produces hydrogen ion or maybe hydronium H3O plus in water, and 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 then polyprotic. So many protons, many hydrogens have more than one hydrogen that will break apart. And so, but this because something has hydrogens does not necessarily mean it's going to break apart. So keep that in mind. And usually the first one is the stronger one. So for instance, H2SO4, sulfuric acid, the first hydrogen is strong, the second hydrogen is weak, for instance. And base is something that forms hydroxide ion in aqueous solution. So this is the Arrhenius definition. Arrhenius definition is acid forms H+, base forms hydroxide. And some properties of the acids. Acids taste sour, bases taste bitter, for instance. And later on, we'll talk about salts. How does salt taste? Is salt bitter? Is salt sour? And the answer is no. Salt tastes salty. Taste is a chemical reaction on our taste buds. So that means that salt, sodium chloride salt, is no longer an acid nor a base. So when acids and bases react, they neutralize. They no longer have the properties of acids and bases. So these are neutral. Like I just mentioned, that neutralization reaction because they are no longer acids and bases. And the net ionic equation for all acids and base reactions is relatively boring. It's hydrogen ion plus hydroxide ion makes water. And then it usually forms a soluble salt. And I mentioned before about the hydronium. This is something, it's hard to tell. By computer simulation, it looks like we don't see any free H plus in solution. But free H plus is just a proton. It doesn't have any electron around it. And it's like one of these questions of how do we know? This is something we may not ever be able to actually determine if there's free hydrogen ion in solution because the hydrogen ion doesn't have any electrons that we can probe, and probably not going to see any interactions in the proton itself. It's not going to the solution's not going to affect the wave function of the proton. So we may never really know if there is free hydrogen ion or if there is only hydronium ion in solution. But because of that, we also, as chemists, we use it interchangeably. And why is that? It's just easier to think of things of one atom instead of four. Is honestly the main reason for that. It makes the equations easier. And bases form hydroxide. And you can form hydroxide, and this is something we'll talk about the Bronsted-Lowry theory in future chapters about how you can have proton donor, proton acceptor. And the idea is with acid base, the hydrogen ion from the acid combines with the hydroxide from the base, and it makes water. And the general formula is acid plus base makes water and a salt. And I told you salt is neither an acid nor a base. Well, in future chapters, some salts do have acidic and basic properties, but this is the intro. We will talk about the more complicated stuff later, but just so you know, that's coming in the future. So acid-base reaction, and you have hydrochloric acid and sodium hydroxide makes water and sodium chloride. And we're showing the hydrogen ion instead of as a hydronium ion in solution. So H3O plus, that's the positive charge coming from that. And the general idea with an acid, acids tend to add positive charge, bases tend to add negative charge. That's another way you can think of acids and bases. And some common acids. So hydrochloric acid, sometimes called muriatic acids, if you've heard of that. Hydrobromic, hydrotic, nitric. Nitric's kind of nasty. It tends to make explosives. Sulfuric acid, sometimes called battery acid. It's what's in lead acid batteries. Perchloric acid, these tend to make explosives, so you're going to have a hard time finding nitric acid and perchloric acid anywhere sitting around because of the explosive nature of the acids. Formic acid, that's from ant bites, so that's where the formic, the Latin for ants. Acetic acid, that's vinegar. Hydrofluoric acid, nasty stuff. It is a weak acid. It dissolves glass and can dissolve your bones. So I'm very afraid of hydrofluoric acid. Common bases, sodium hydroxide, sometimes referred to as lye, L-Y-E, lye, and lithium hydroxide, potassium hydroxide. Calcium hydroxide, sometimes referred to as lime, L-I-M-E, lime, and barium hydroxide. Ammonia is also a weak base. So whether or not, well, we'll talk about strength of acids and bases later in future chapters. So titration is a way of figuring out how much stuff is in stuff. So we take something that we know its concentration, the titrant, and it's reacted with something that we don't know how much stuff is in it, and it's called the analyte. And then we react it to the equivalency point, and then from that we can determine by back calculating it, and since we know the concentration of the titrant, we can figure out how much of the analyte we have. This can be done via something like a pH probe, but in old school chemistry we use an indicator. An example of an indicator is phenolphthalein. It usually uses that pink color. So we have an acid and we add a known concentration of base, and then we know that it's completely reacted when it forms the pink color. Oh, and shown here is here's the phenolphthalein. Actually, the one on the far right, that person's gone a little too far. It's usually a paler pink than that hot pink color. So let's look at this one here. When you have 10 milliliters of a 0.2 molar hydrogen bromide solution is titrated with 0.1 molar sodium hydroxide. What volume of sodium hydroxide is required to reach the equivalency point? So don't forget, these are different concentrations. It's a 1-to-1 stoichiometric ratio because it's one hydrogen, one hydroxide, one hydrogen in the hydrogen bromide, one hydroxide in the sodium hydroxide, but it has twice the concentration. So the hydrobromic acid is got twice the concentration. Therefore, you need twice as much sodium hydroxide. So it's going to need 20 milliliters. Okay, moving on, talking about gas evolution reactions. For instance, we have sulfuric acid with lithium sulfide makes lithium sulfate and hydrogen sulfide gas. Hydrogen sulfide gas smells really, really badly. Smells like rotten eggs. And we as humans, we can smell sulfur in the -2 oxidation state. We'll talk about oxidation states soon. We can smell sulfur specifically in that state in the parts per trillion range. So we're very sensitive to this. So we it's a strong smell and we tend not to like it. So and there's other ones. So hydrochloric acid plus sodium bicarbonate makes sodium chloride salt, and well, it forms intermediate carbonic acid, and then that will further go and break apart and form water and carbon dioxide. So that's also how we dissolve carbon dioxide in our blood. It actually, the sugar burns in our mitochondria, and then it dissolves to form carbonic acid, and then it brings us to that via our bloodstream goes to our lungs, and then we exhale carbon dioxide. I don't know if the closed caption, I was exhaling. So here's some more. Well, here's the acid and baking soda chemical reaction. We have bicarbonate and hydrochloric acid, and it forms bubbles of CO2. So it fizzes, and that's the bubbles. That's the gas evolution reaction. So here's some types. Sulfides. react with acids to form hydrogen sulfide. Carbonates and bicarbonates, remember bi means extra hydrogen, so carbonate is CO3, bicarbonate is HCO3, forms carbon dioxide. Sulfites and bisulfites make SO2, also gives me a headache, SO2 gas. And ammonium ions form ammonia gas. And by the intermediate, you can form molecules like so carbonic acid, H2CO3, and H2SO3 and ammonium hydroxide. So these are intermediates. That's sulfurous acid. Sorry, I should tell you what it is. These are intermediates that it keeps it dissolved in water, then further breaks apart to form the other stuff. And moving on, we're going to talk about oxidation reduction reactions. And getting there, we'll talk about oxidation numbers. It's a way of keeping track of where electrons are. So in oxidation reduction reactions, oftentimes just called redox. So oxidation means the loss of electrons. Reduction means the gain of electrons. So whenever you have one, you have the other. So they always happen together. And so we could call it the ox-red or redox. We decided to call it redox. So reduction, oxidation, oxidation, reduction. So redox just means that we're shortening it and we're saying they're coming together. So for instance, 4 irons plus 3 oxygens make 2 Fe iron 3 oxides, and this is rust. This is a transfer of electrons from iron to oxygen. Oh, and I guess the most common oxidizer is oxygen. So iron here is oxidized. What does it mean? It's added oxygen to it. Likewise, here you have octane oxidized with oxygen in a combustion reaction. And we have another one, hydrogen and oxygen to form water. So you're literally adding oxygen, and that's the oxidation reaction. So combustion is an oxidation reaction, and we'll talk about oxidation states later. In this case, hydrogen gives electrons to oxygen, and this is very exothermic. So combustion are exothermic reactions. So oxidation, as I said before, is a loss of electrons. Reduction is the gain of electrons. So in this case, sodium reacts with chlorine to form sodium chloride. And sodium is losing an electron, chlorine is gaining an electron. So chlorine, I mean one chlorine atom. I know a chlorine molecule is gaining 2 electrons in this case, but the chlorine atom is in general gaining 1 electron. And for this, it doesn't necessarily have to be a complete transfer. So you can have, with oxidation states, we often just say, we say that the more electronegative atom, we haven't talked about electronegativity, and I know I'm teasing the future things, the more electronegative atom gets all the electrons. So we'll cover these rules later about electronegativity. But in this case, the chlorine and hydrochloric acid, the chlorine tends to draw more electron density to itself than the hydrogen. And this is not a complete transfer. The hydrogen still gets some electron density, but not as much. And I'm using the word electron density because electrons, they can be in many different places at once. And so an electron can spend 30% of its time with hydrogen and 60% or 70% of the time with chlorine or something like that. And I'm just kind of making these numbers up, but it just splits. It'll occupy space, and it'll just occupy space sometimes around hydrogen, sometimes around chlorine. Well, I mean it's occupying at the same time, but it's the size of its wave function, the size of the cloud is different. So it's smaller on hydrogen and it's more on the chlorine, I should say. And we can have oxidation reduction without combustion. So already mentioned with the sodium chloride, you're having transfer of electrons with that. And this is a very exothermic reaction as well. And metals react with non-metals, and the idea is that the reaction that the transfer of electrons, the metal is transferring electrons to the non-metal. And it turns those elements into ions. So I mentioned this before about oxidation states. We need a way to keep track of these states, so keep track of where electrons are. and we give them the name oxidation state or oxidation number. And then the ion behaves very differently. So to give you an example, that chromium metal, chromium plus 3, and chromium plus 6. So chromium metal and chromium plus 3 oxidation state, these are very safe compounds. Well, chromium metal, it's not a compound, it's an element, but these are safe. Chromium plus 6, though, this stuff is a carcinogen. So chromium in this plus 6 state is very dangerous. So these oxidation states do mean things, and they have very real examples. So we'll go over the rules, and it's kind of like the charge. And I'm kind of hinting at before with the chromium, saying it's the plus 6 state. It's the charge. It's as if the chromium has 6 electrons removed from it. And the positive means electrons taken away, and negative means electrons added. So sometimes the negative signs are written before or after. So it's the oxidation states are imaginary charges, but it's our way of bookkeeping. Ion charges are real, and oftentimes the charge is written after. So here are the rules, and these are hierarchical, meaning that rule number 1 is more important than rule number 2. So free elements have an oxidation state of 0. And this is for any combination of elements. Ozone, O3, oxygen is said to have an oxidation state of 0 in the ozone molecule, for instance. The free element, just one element, that has an oxidation state of 0. Monatomic ions, so that means an ion with one atom. Those are equal to charge. So sum of oxidation states for all atoms in a compound is 0, and for an ion is equal to their charge. So nitrate ion, for instance, the sum of the oxidation states of nitrogen and 3 times the oxygen is equal to -1. And you can see here that is why, so nitrogen is forced to be a +5. So we give the nitrogen the +5 state. So then alkalis tend to be +1 in molecules. Alkaline earths tend to be +2. Rule number 4. Rule number 5, we have this chart where fluorine tends to be -1, hydrogen tends to be +1, oxygen tends to be -2, halogens tend to be -1, oxygen family tends to be -2, nitrogen family tends to be -3. And so, like I said, these rules are hierarchical, and you can have other oxidation states. So oxygen, for instance, can have a -1 state. We call those peroxides. We can also have fractional oxidation states. So oxygen to the -1/2 state is known as a superoxide, for instance. And peroxides and superoxides tend to be explosive, so watch out for those. And okay, so keep these in mind. The oxidation state of the element depends on the other element that are present. So the exception, of course, the alkalis and the alkaline earths. So those tend not to change very frequently. And you have the hierarchy rules. So don't forget the hierarchy rules. That's the rule 5 at the chart, but that's lower in the hierarchy. So oftentimes you're going to use rule number 3. That's the sum of the oxidation states is 0 for a neutral molecule or formula unit, and then equal to the charge for a charge. So, and then oxidation states that are not covered by the rule, you have to use the sum of those, like I just mentioned, rule number 3, and then determine the oxidation states based off of the other rules. So these are puzzles. So oxidation is an increase in oxidation state. So increase means more positive, which means loss of electrons. Reduction is a decrease, means adding more negatives, adding more negative charge. That is addition of electrons. So if you look at this reaction here, carbon plus 2 sulfurs makes carbon disulfide, and carbon goes from a free element to a +4 oxidation state in the molecule. And notice that in sulfur also is the 0 oxidation state starting off, but then in carbon disulfide, it ends up being a -2, and those 2 -2s counteract the carbon +4. So this is the oxidation state is just a way of keeping track where the electrons go. In this case, we're saying that the electrons are going from carbon and they're moving over to sulfur, although that is a molecule. They're actually all sharing them, but this is one of those unequal sharing. And carbon is oxidized, it loses electrons. Sulfur gains electrons, it is reduced. And they have to happen simultaneously, the oxidation reduction reactions. If one atom loses electron, the other atom has to take them in. And the specifically, this is kind of, I know students have a hard time with this. The reactant that causes reduction is called the reducing agent. It's actually the one that's oxidized. And the reactant that causes oxidation is the oxidizing agent, but it does that by being reduced. So oxygen is a great oxidizer. Oxygen is always being reduced. So how is the oxidizing agent? I always think of James Bond. James Bond is the agent of death. He delivers death, right? So the reducing agent delivers reduction. How does it deliver reduction? It gives up electrons. The oxidizing agent delivers oxidation. How's it deliver oxidation? It takes electrons away. So think of it that way. That's kind of, I always thought about James Bond, right? He's always doing the killing. He never dies. He's delivering the death. So hopefully that's not too morbid of an example for you. So guidelines for these oxidizing reducing agents. So whenever there's a change in oxidation states, you have to look to see where the electrons are going. The oxidizing agent oxidizes the other substance and is reduced, and the reducing agent is oxidized. So, as I mentioned before. And let's talk about spontaneity. The activity series of metals, and this is an empirical, so experimental. We've gone through this. Generally, the metals that tend to undergo oxidation, these are the most reactive, and the metals that are least likely to go under oxidation tend to be the least reactive. And also vice versa, if you have a metal and that tends to undergo oxidation, that solution is very unreactive. So halide solutions, these tend to be very unreactive. Alkali solutions. Alkali solutions. They tend to be very unreactive, very noble. And then gold and silver solutions, though, the gold and silver, they tend to be very non-reactive. But then the solutions of gold and silver tend to be very reactive because gold likes to grab its electrons back. So, we show the oxidation and or reduction as half reactions. So it'd be very common. Just look at half the reaction and you see where they tend to go. And I mentioned there the half reactions at the bottom tend to go in the reverse direction. The solutions are very reactive. So here, the most active is lithium. Lithium is a very active metal, and it's got a very strong reduction potential. So I should say very weak, but it's very, very, very negative. It's easy to oxidize. When the bottom, gold tends not to oxidize very easily. But the converse is, if you have a gold or silver solution, these solutions are very reactive. They react with metals. And notice something here that we have hydrogen. Hydrogen is the reference point. It's listed in bold. That's the reference point. We reference things to hydrogen. And because of that, the metals below are the ones that tend not to dissolve in acids. Although you can get copper, silver, and gold to dissolve in acids, it's just hard. Copper will dissolve and silver too, will dissolve in nitric acid. Gold, you have to use a different one. Gold and platinum, you have to use aqua regia, which is a mixture of hydrochloric and nitric acid. It's very difficult to dissolve gold. It can do it. It can be done, but it's very difficult to do. And we're done. See you next chapter.